This introduction is about the physics and modeling of linearized, time-invariant dynamic systems. So we then talk about systems with energy storage. And you could say it as such: a system in which energy is stored, which is not in the quiescent state, to which no excitations are applied, tends to its quiescent state, in which the energy is either distributed over system parts, dissipated in system parts, or radiated by system parts. But this is only true if you have distributed systems in which the wavelength is let's say, shorter than the length of connections, put it this way. We model such systems with differential equations, and for symbolic analysis, we can only deal with a limited number of types of differential equations. And usually this is linear normal differential equations with fixed coefficients. Normal means no partial differential equations, so no distributed systems, lumped systems only. So to this end, we need to model the system as lumped, linear, and time invariant. So if the system does not behave as such, this would of course be a wrong model. So we are looking to systems that behave as such. Well, amplifiers usually need to behave as such. They are linear and time invariant, and we make them with networks, electrical networks, and are usually considered as lumped systems. In electronics, we call this usually small signal analysis of stationary lumped circuits. So let's go to how we describe such systems. We model them with linear differential equations with constant coefficients. Constant means they do not vary with time, so it is not a time variant system. So the number, the structure of such equation is that the sum of a number of derivatives of the response equals the sum of a number of derivatives of the excitation, like this, in which the response is yt and the excitation is xt, an input signal. Of course, there can be more input signals, but this is just a one input, one output system. So the solution of those equations is usually an exponential function, because exponential functions retain their shape under differentiation and integration. And we solve them usually either with Fourier, we write the signals as sum of imaginary exponentials, or as Laplace, we write them as sum of complex exponentials, like this. And if we then substitute this in the differential equation, the differential equation transforms to an algebraic equation. So, and then we have an algebraic equation and can define a transfer function, which is a transfer from a complex exponential at the input to a complex exponential at the output, and or both in Laplace and in Fourier domain, of course.